All right, let's dive right into this. Welcome to The Explainer. Today, we're unpacking the absolutely fascinating, totally foundational concepts of machine learning, starting straight from Unit 1. If you've been wanting to really understand the engine that is currently driving, this entire modern technological revolution, you are in exactly the right place. And we're not just talking about minor upgrades to your everyday software here. We are talking about a total paradigm shift in computing. I mean, right now, as we speak, algorithms are diagnosing complex diseases with higher accuracy than panels of human doctors. They're navigating self-driving cars safely through chaotic, unpredictable city streets. They're even helping discover entirely new antibiotics. So this explainer is designed to lay down the absolute bedrock of what machine learning actually is, how it functions under the hood, and why it so profoundly matters. We're going to go really deep today, unpacking every single major concept to set the perfect stage for everything else we'll cover later on, especially as we look forward to getting into the mathematical weeds of supervised learning algorithms in Unit 3. So let's get started.
So here is the fundamental question we are answering today. And honestly, it completely changes how we think about computing. Historically, computers were they were incredibly fast calculators. You gave them a strict, inflexible set of rules, and they followed them, period. But how do we get a machine to actually learn something it wasn't explicitly told to do? Our source material beautifully defines this using a classic framework. Basically, a computer program is said to learn from experience, let's call that E, with respect to some class of tasks, T, and a performance measure, P, if its performance at tasks in T, as measured by P, improves with experience E. Okay, that sounds like a lot, so let's break that down because it's absolutely crucial. Think about a robot driving a car. The task T is the act of driving on highways using vision sensors. The performance measure P, that might be the average distance the robot travels before it makes a mistake or swerves out of its lane. And the experience E is a massive sequence of images and steering commands recorded while observing a human driver. So, as the machine processes more experience, literally just more hours of driving data, its performance on the task improves. Pause and just think about that for a second. We aren't programming the rules of driving. We are programming the ability to learn the rules of driving. It's a completely different paradigm.
To unpack all of this, we're going to follow a really clear what, how, where framework today. First, what is machine learning? Second, the 3 learning types. Third, the ML life cycle. Fourth, real-world applications. And finally, we'll wrap up with the key takeaways to make sure it all sticks. Let's start with the what. How exactly do we define this revolutionary technology? Okay, so the crucial point here, the thing you really need to remember, is without explicit programming. Machine learning is a branch of artificial intelligence that enables algorithms to uncover hidden patterns within datasets. It allows them to make predictions on new, similar data. To really grasp this, imagine you're looking at a spreadsheet with 10,000 rows of numbers. As a human, if you stare at that, it just looks like a massive blur of data. Your brain can't easily connect row 52 to row 9,000. It's just too much. But to a machine learning algorithm, that spreadsheet isn't a blur at all. It's a crystal clear map. It can instantly find the hidden patterns, the tiny correlations, and the exact paths connecting those numbers. Traditional machine learning combines this kind of intense data analysis with statistical tools to predict outputs, yielding actionable insights. We aren't giving the computer a rigid step-by-step mathematical proof to follow anymore. Instead, we're giving it a massive amount of data and basically asking it to figure out the rules on its own. Let's compare the two directly to really lock this concept in. Think of traditional programming like giving a computer a highly detailed recipe. You give it the ingredients, which is your data, and you give it the exact recipe, which is the program. The computer executes the recipe and gives you the cake, which is your output. Simple, right? But think about how absurdly difficult it would be to write a traditional software program to visually identify a cake. You'd have to write code like, if the shape is round and the color is chocolate, then it is a cake. But what if the cake is square? Boom, your program fails. What if it's vanilla? Your program crashes. You would literally spend the rest of your life writing exceptions to the rules. Machine learning flips this entirely. It's like giving the computer thousands of pictures of all different types of cakes, along with a list of ingredients, and letting it write the recipe itself. We input the data and the desired output, and the machine learning algorithm gives us the program, the underlying rules as the result. It learns what cake miss looks like intrinsically. Now, what makes these systems so incredibly powerful in practice? Our source outlines 6 important features, and each one beautifully builds on the last. First up, learning from data. Algorithms aren't explicitly programmed for every scenario. A spam filter, for example, learns to identify spam not because a human wrote a dictionary of bad words, but by analyzing a massive data set of labeled emails, recognizing complex, constantly shifting text patterns. Second, adaptability and self-improvement. This is where the magic happens. Models get better over time. A recommendation system like Netflix constantly refines its suggestions based on your ongoing viewing history. If your tastes change, the model adapts right along with you. Third, handling large volumes of data. This is huge. If you throw a billion rows of data at traditional software, it bogs down or crashes. But machine learning, it thrives on it. It actually gets smarter with more data. Fraud detection systems in banks process vast numbers of global transactions in real time to flag suspicious activity without even breaking a sweat. Fourth is automation of repetitive tasks. Chatbots can handle complex, multi-step customer service inquiries like order tracking and returns, freeing up human agents for the nuanced issues. Fifth, personalization. Algorithms analyze your highly individual behavior to deliver tailored experiences. Think about a music streaming service building a customized playlist that feels like it literally read your mind. And finally, solving complex problems. Machine learning excels at tackling things traditional programming simply can't touch, like identifying the earliest, faintest signs of cancer in medical imaging with accuracy rates that often surpass leading human specialists. So, now that we know what it is and what its features are, let's look at the how. We're going to explore the 3 primary ways these algorithms actually learn. There are 3 main pillars here: supervised, unsupervised, and reinforcement learning. And they differ in some really fundamental ways. Let's think about the type of data they use. Supervised learning requires labeled data, meaning we know the answers beforehand. We are explicitly guiding it. Unsupervised learning, on the other hand, uses completely unlabeled data. We just throw a bunch of raw information at the machine and it's on its own. And reinforcement learning, it has no predefined static data set at all. It interacts directly with a live environment. Because of this, the underlying algorithms differ wildly. For supervised, we use tools like linear regression, which essentially draws a line of best fit through data points, or support vector machines, which draw mathematical boundaries between categories. For unsupervised, we use things like principal component analysis, or PCA, which squishes highly complex, multidimensional data down to its most important parts so we can understand it. And for reinforcement, we use Q-learning to teach systems a series of actions based on a point system. Let's look at each one of these 3 pillars a little closer. Let's focus on supervised learning first. The way this flows is you feed raw input data into an algorithm alongside the correct answers. It acts almost exactly like a teacher supervising a student. The algorithm iteratively makes predictions on the training data and is corrected by the teacher. Learning stops when the algorithm achieves an acceptable level of performance. Our source provides a really great example here. Imagine data regarding patients entering a clinic. The data consists of the gender and age of the patients, and critically, each patient is already labeled as either healthy or sick. So a 48-year-old male is labeled sick, a 53-year-old female is labeled healthy. The supervised algorithm studies this exact pairing. How does it learn? By looking at the mathematical distance and relationships between these known labeled data points. So when a brand new, unseen 50-year-old patient walks in, the algorithm can predict their health status based on how closely their data aligns with what it learned from all those previous labeled examples. In stark contrast, unsupervised learning is entirely self-guided. There's no teacher, and there are absolutely no correct answers provided. It acts like an explorer organizing a messy room, finding hidden associations and clusters all on its own. Let's extend that clinic example. Imagine patients walking in with their gender, age, and a dozen different blood test results. But this time, we do not tell the computer who is healthy and who is sick. The data is totally unlabeled. The unsupervised algorithm will simply look at the inputs and try to find structures. And here is the real aha moment for this technology. What if the algorithm groups patients together and discovers a brand new symptom cluster, like a specific combination of age, blood pressure, and a protein level that human doctors entirely missed? It finds groupings we didn't even know existed. This is exactly why unsupervised learning is so heavily used in exploratory data analysis and massive scientific discoveries. And the third pillar is reinforcement learning. This is the problem of getting an agent to act in the world so as to maximize its rewards. The learner is not told what actions to take. Instead, it must discover which actions yield the most reward by just trying them out. It's honestly exactly like training a dog with treats. We can't explicitly tell the dog mathematically how to sit, but we can reward it if it does the right thing or penalize it if it does the wrong thing. In the most interesting and complex cases, an action might affect not only the immediate reward, but also the next situation and all subsequent rewards. This is the whole concept of delayed rewards. Think about a game of chess. Moving a single pawn one space forward might seem totally insignificant right now. There's no immediate reward. But that single move might set up a trap that allows you to achieve checkmate 10 moves later. The algorithm has to learn to value that long-term payoff. This trial and error method is exactly how we train computers to play insanely complex games like Google's AlphaGo, and how we teach bipedal robots to walk and balance. Okay, let's move to the mechanics and see how all of this builds into a complete functioning system. We know the learning types, but how does a real project get built from scratch? Let's explore the machine learning lifecycle.
If you map out the continuous, complex journey of a learning machine, it starts from raw input data and goes all the way to a final prediction engine. It starts with input data. This could be highly structured spreadsheets or entirely unstructured text and images. Then it hits data processing. This step is absolutely critical. You have to clean the data, handle missing values, and standardize the formats. If you put garbage in, you get garbage out, right? Then we move to feature selection, which is all about reducing dimensionality. Now, what's really interesting about this concept is how incredibly practical it is. Dimensionality reduction simply means throwing out useless data. If you're trying to predict a patient's risk of heart disease, you want their blood pressure and their age. You do not care about their hair color. Throwing out hair color reduces dimensionality, so the model doesn't get overwhelmed with noise. Next is model selection, where we pick the actual algorithm. Then the actual training of the model occurs, followed by rigorous evaluation using test sets. If the evaluation isn't good enough, we loop back into model optimization. Only after optimizing do we get the final ML model, which is plugged into the prediction engine to process completely unseen data in the real world.
So we can distill that massive process into these critical sequential steps. The ML lifecycle is a highly structured, deeply iterative process. You gather and prepare, you select your features and your algorithm, you train. But the real magic happens in evaluation and hyperparameter tuning. You don't just train a model once and call it a day. You test its performance and then you tune it. Think of hyperparameter tuning kind of like the dials on an oven. Let's say you baked a cake, which represents training your model, but it came out a little too dry. You don't throw away the whole recipe. Instead, you adjust the temperature dial, the hyperparameter, and you try baking it again to squeeze out a better result. You iterate. It's a loop that continuously builds momentum, reducing errors and improving accuracy before the model is finally deployed. So, we know the what and we know the how. Now let's explore the where. Where is this actually happening? Let's look at the real-world impact. Before we list the specific applications, it's really helpful to contextualize machine learning within the broader tech landscape. Imagine a set of nested circles. Artificial intelligence is the broad, overarching field of making computers smart. Inside that is machine learning, the specific approach of using data to learn without explicit programming. Inside that is deep learning. Deep learning is just a highly specialized inner circle of ML that uses massive layered structures inspired by the human brain, called neural networks. And intersecting all of these is data science, which is the overarching practice of extracting knowledge from data. Machine learning is the vital, beating heart bridging traditional AI goals with the raw analytical power of data science. And because it sits at that vital intersection, the sheer versatility of machine learning is just staggering. Let's look at a few of these in depth. Take product recommendations on Netflix. They use something called collaborative filtering. It works like this. The algorithm notices that you and a total stranger on the other side of the world both loved movie A and movie B. It recognizes a pattern in your tastes. If that stranger then watches movie C and gives it a thumbs up, the algorithm will instantly recommend movie C to you, predicting you'll feel the exact same way. In finance, fraud detection relies on ML's ability to process massive volumes of data instantly. When you swipe your credit card, an algorithm looks at thousands of data points, your location, the time of day, your purchase history, the merchant's history, literally in milliseconds. If a purchase happens in another country 10 minutes after you bought coffee locally, the algorithm immediately flags it as an anomaly. And in medicine, learning programs process thousands of historical medical images to learn the exact pixel variations that indicate early-stage tumors. They can diagnose critical illnesses by spotting patterns in an MRI that are completely invisible to the human eye. There's a great quote from our source material that says, "Machine learning can process large amounts of data quickly, generating insights and predictions that would take humans much longer." This really captures why all of this matters so profoundly. I really want to emphasize the idea of bypassing human limits here. It's not just that ML can do things we can do, just a little faster. It provides speed, scale, and pattern recognition that entirely bypasses human limitations altogether. The volume of data in fields like physics, astronomy, or just browsing the internet is simply too huge for the human brain to comprehend.
Searching for relevant information and making complex decisions rapidly across a billion variables cannot be done manually anymore. Machine learning introduces a completely new cognitive scale. It is the necessary tool for the modern data age.
Let's wrap up this explainer. We've covered a massive amount of ground today, going deep into the foundational mechanics of this technology. So let's distill it down to the absolute most critical concepts you need to remember from Unit 1. Remember these 4 pillars moving forward. First, the core definition. Machine learning enables systems to find hidden patterns and make accurate predictions without explicit programming. It learns from experience, constantly adapting and improving its own rules. Second, the 3 main learning categories. Supervised learning uses labeled data to guide the machine like a teacher. Unsupervised learning finds entirely hidden, novel structures in messy, unlabeled data. And reinforcement learning relies on interaction and delayed rewards, mastering complex environments through trial and error. Third, remember the process is not magic. It follows a strict, highly iterative life cycle of data preparation, dimensionality reduction, feature selection, training, evaluation, and hyperparameter tuning. And finally, its real-world footprint is absolutely massive, driving modern AI applications across finance, medicine, entertainment, and robotics. It's an incredible foundation we've laid down today, but as we see just how adaptable, scalable, and self-improving these systems are, it leaves us with a thrilling question to ponder. As machine learning models continuously ingest massive amounts of data and refine their own rules, what limits actually exist on what they can teach themselves next? Keep that sense of wonder and that question in mind as we move forward into the future units, where we will really get into the mathematical weeds of the supervised algorithms in Unit 3. Thanks for joining me on The Explainer, and keep learning.
Welcome to The Explainer. Today we're tackling a massive, and I mean absolutely crucial milestone in our machine learning journey, Unit 2. We are going to pull back the curtain and show you exactly how messy, chaotic, real-world data is completely transformed into a pristine, optimized format that machine learning algorithms just absolutely love. You see, the models we're going to build later on, they're really only as good as the data we feed them. It's the classic rule. If you feed an algorithm garbage, it's going to give you garbage predictions right back. So how do we actually take the chaos of the real world and compress it into elegant mathematics? Well, let's find out.
Okay, let's just dive right into a really big question. What happens when your data set has 1,000 or even 1,000,000 columns? Just try to imagine finding a meaningful pattern in a spreadsheet that massive. As human beings, our brains kind of start to melt past 3 or 4 variables. But even for computers, this introduces a devastating roadblock. It's known as the curse of dimensionality. As you add more and more features, like, say, tracking every single pixel in a high-res image, or every single word in a massive document, the volume of the mathematical space you're working in grows exponentially. This makes your data extremely sparse, it drastically slows down your training times, and honestly, it can hopelessly confuse your models. To build powerful predictive engines, we absolutely have to slay this beast.
So here is our roadmap to getting that clean, high-performance data. First, the dimensionality problem. Second, treating datasets as matrices. Third, the data preprocessing pipeline. Fourth, feature selection versus feature extraction. And finally, demystifying principal component analysis.
All right, starting with Section 1, the dimensionality problem. Let's tame this data beast.
Here's the formal definition. Dimensionality reduction is the process of transforming high-dimensional data into a lower-dimensional space that preserves the essence of the original data. Now, the absolutely crucial point here is that we aren't just blindly deleting columns and tossing out valuable insights. Think of it like packing a suitcase for a long trip across the world. You literally can't take your entire closet with you, right? It's way too heavy and it's too expensive to carry. Instead, you strategically pack a few highly versatile items that mix and match to give you the total essence of your wardrobe. Dimensionality reduction does exactly this, but mathematically. We strategically shrink the number of features while making sure all the underlying patterns and important information remain completely intact.
Moving right along to Section 2, Datasets as Matrices. It's time to map the terrain.
Imagine you're looking at a sample dataset from a local clinic. We see the clinic's records where every single person who walks through the door has their gender, their age, and a label stating whether they are sick or healthy recorded. Now, to a human doctor, this is just a standard patient log. But to a machine learning model, the concepts of male or 48 years old are just text and numbers. A computer views this entire table simply as a matrix, a structured, mathematical grid that is just waiting to be processed. Transforming our real-world problems into these perfectly organized grids is really step 1 of the magic.
To actually navigate this matrix, we have to break it down into two fundamental building blocks, the row vector and the column vector. A row vector reads from left to right. It represents a single instance. So in our clinic example, one single patient's complete profile, their age, their gender, their health status, that forms one row vector. On the flip side, a column vector reads from top to bottom. It represents a single feature across all the different instances. For example, a column vector containing literally everyone's age. By breaking the data set down this way, we're basically creating a mathematical map. We can now tell the algorithm things like, hey, compare this column vector to that column vector to find a trend, or cluster all these similar row vectors together.
Which brings us nicely to Section 3, Data Preprocessing, the all-important cleaning pipeline. This preprocessing builds into a very structured workflow. Step 1 is data cleaning. Say a patient forgot to write down their age on the intake form. Well, now we have a missing value. We might fix this by imputing the data. Maybe we just fill in that blank with the average age of all the other patients, just so we don't have to throw their whole medical record away. We also use this step to smooth out noisy data and handle any crazy extreme outliers. Step 2 is data transformation, where we normalize and standardize our variables to make sure they're all playing on an equal field. And finally, step 3 is data reduction, where we actually apply our dimensionality reduction techniques to compact the data set down.
Understanding exactly why step 2, the transformation step, is vital is super important here. Think about column standardization for a second, which ensures fair feature contribution. Imagine you're building a machine learning model to predict housing prices. One of your columns is the number of bedrooms. Let's say it ranges between 1 and 5. Another column is the property size in square feet, which ranges between, say, 1,000 and 5,000. If we just blindly dump these raw numbers into an algorithm, the algorithm is going to look at the massive numbers in the square footage column and completely ignore the bedroom column. It just naturally assumes bigger numbers must be more important. Standardization forcefully scales all those columns down so they share a very similar range, often setting them to a mean of 0 and a standard deviation of 1. This guarantees, absolutely guarantees, that no single feature unfairly dominates the learning process just because its raw numbers happen to look bigger.
All right, Section 4, Feature Selection versus Feature Extraction. How do we choose our strategy?
The differences between these two strategies are literally night and day. Feature selection is pretty much exactly what it sounds like. You evaluate all your current features, and you simply select a subset of the most relevant ones, throwing the rest straight in the trash. You keep the original features, you're just using fewer of them. Feature extraction, on the other hand, is way more radical. It actually transforms the raw data into a brand new set of features that are much more informative and compact. It extracts the essential information from all the original features and mashes them together to represent them in a lower dimensional space. Think of it like this. Feature selection is like picking the 3 best athletes on a basketball team to go play a 3-on-3 game. Feature extraction is like somehow fusing the entire team together in a lab to create 3 brand new super-powered synthetic athletes. Wild, right? Now, if you do decide to go the feature selection route, picking the best original columns, you generally use one of 2 iterative processes. In forward selection, you start with absolutely 0 variables. You test them all and you add the single best one. Then you test the rest again and add the next one. That decreases the model's error the most. You just keep building up and up until adding more variables doesn't actually help anymore. Backward selection is the exact opposite approach. You start with the entire massive data set of all your features. Then, step by step, you find the most useless feature and you remove it. You keep trimming the fat until taking away another variable actually starts hurting the model's overall performance. Both methods are great, but sometimes, merely selecting existing features just isn't powerful enough. Sometimes we really need extraction.
And that brings us to the climax, Section 5, Demystifying PCA, the ultimate superpower.
So how does PCA, Principal Component Analysis, actually work? Imagine a cloud of data points plotted out in space, forming roughly an oval or an ellipse shape. What PCA does is map the data from a higher dimensional space to a lower one, but with a very specific strict condition. It absolutely must maximize the variance. Now, variance is just a fancy mathematical word for spread or information. PCA essentially draws an axis right through the absolute longest spread of that data cloud. That specific line becomes our new feature 1. Then it draws a second axis orthogonal, meaning at a perfect 90-degree right angle to the first one, capturing the next largest spread. These brand new axes are what we call principal components. We have literally rotated our mathematical universe to squish the data into its most informative angles. Instead of getting totally bogged down in dense linear algebra, just try to remember this one brilliant intuition. The first principal component is a mathematically constructed super feature that captures the absolute most variation in the data possible. Why? Because in machine learning, variation equals information.
If a feature has no variation, say every single patient who walks into that clinic is exactly 48 years old, well, that feature tells us absolutely nothing useful for making future predictions. By actively hunting for the axes of maximum variation, PCA ensures that even as we drop from, say, 100 dimensions down to maybe just 5 principal components, we are still retaining the vast majority of the critical information needed to properly train our models.
There is a very good reason the sheer utility of PCA makes it a staple in literally every data scientist toolkit. It provides massive data compression, which drastically speeds up processing times. It inherently acts as noise reduction too. Because the random, annoying noise in your data usually doesn't have much structural variance, it naturally just gets dropped when we only keep the top principal components. It also elegantly solves something called multicollinearity, which is when two features are highly correlated and end up confusing the model by transforming them into totally uncorrelated orthogonal components. And honestly, perhaps best of all, it allows for amazing data visualization. If you have a data set with 50 dimensions, you obviously can't graph it. But if you use PCA to compress it down to its top 2 or 3 principal components, you can easily plot it on a standard 2D or 3D graph and actually visually see the clusters with your own 2 eyes.
But hey, there's no such thing as a free lunch in machine learning, right? PCA definitely does come with some pretty significant disadvantages. Remember earlier when I mentioned that feature extraction creates totally new synthetic features? Well, that makes interpretation incredibly difficult. If a model predicts someone is sick based on principal component 1, a doctor is obviously going to ask, well, what exactly is principal component 1? And you'd have to look at them and say, well, it's a mathematical combination of 0.2 times their age plus 0.5 times their blood pressure minus 0.1 times their weight. It completely loses that human readability. Furthermore, remember our data pipeline? PCA is violently sensitive to data scaling. If you forget to standardize your data first, PCA will completely fail. It'll just lazily latch on to the feature with the biggest raw numbers. It also assumes relationships are purely linear, and if you drop too many components, you run a very real risk of actual information loss.
Ultimately, mastering Unit 2 means realizing a fundamental truth. Good machine learning isn't just about throwing flashy, complex algorithms at a wall and hoping something sticks. It is entirely about how elegantly you clean, prepare, standardize, and mathematically compress the data before those predictive algorithms even boot up. By conquering the curse of dimensionality, using awesome tools like PCA, we build a sleek, highly optimized matrix of pure insight. But, this leaves us with a pretty fascinating question to ponder. As algorithms become more and more powerful in Unit 3, will there ever be a day when AI just does all this tedious data cleaning for us automatically? Or will human intuition always be required to define the matrix? Keep exploring, keep simplifying, and I will see you in the next explainer.
Welcome to this explainer. Today we are completely demystifying Unit 3, Supervised Machine Learning. Have you ever wondered how your email's spam filter just intuitively knows which messages to block, or how advanced medical software can flag anomalies with startling life-saving precision? Well, if you have, you are in the exact right place. We're heading straight into the engine room of machine learning today to see exactly how raw data gets transformed into powerful, actionable predictions. Let's get into it. Here's our quick roadmap for this explainer. First, we'll define what supervised learning actually is. Then we'll walk through the 6-step supervised learning workflow. After that, we'll break down the difference between regression and classification. Then we'll take a deep dive into the key algorithms you need to know. And finally, we'll wrap up with the summary and a little peek at what's coming next. All right, let's kick things off with Section 1. What is supervised learning? So, by definition, supervised learning is the machine learning task of learning a function that maps an input to an output based on labeled example input-output pairs. Now, I want to put a massive, bright spotlight on that word labeled. This is absolutely crucial. Every single piece of training data you feed the algorithm comes with the correct answer already attached to it. Think of it like a stack of flashcards. You've got the question on the front, and the answer is explicitly written out on the back. The algorithm studies these flashcards, figures out an inferred mathematical mapping function, and eventually learns how to answer brand new questions it has literally never seen before. And really, that's exactly why it's called supervised. It's incredibly helpful to think of the algorithm as a student and the training dataset as a teacher. Because we already know the correct answers, what we call the target outputs, the whole process is like a teacher standing over a student taking a practice test. We feed data into the algorithm, it makes a guess, and then that prediction is strictly compared against the known correct answer. If the algorithm gets it wrong, the teacher essentially says, nope, try again, and corrects it. It's a continuous, rapid-fire loop of trial and error. The algorithm mathematically adjusts its internal gears, trying again and again until it reaches an acceptable level of accuracy. Let's pull that abstract concept down into reality for a second. Consider patient clinic data. We have our inputs.
which in machine learning we call features. And these might be things like a patient's gender and age. Then we have our all-important label, whether that patient is healthy or sick. The algorithm studies thousands of these rows to find the subtle, hidden patterns. It notices exactly how age and gender might correlate with that health label. The ultimate goal here is that when a brand new patient walks into the clinic tomorrow and all we have is their age and gender, the algorithm can accurately predict their health status completely on its own. No human intervention required. That's the magic of it. Moving right along to Section 2, the supervised learning workflow. Any successful supervised learning project follows a rigorous 6-step workflow. You can't really skip these. Let's imagine we're building a system to predict house prices. Step 1 is data collection. You absolutely must gather labeled data. So that's features like square footage paired with the correct output, the actual sale price. Step 2 is data pre-processing. Real-world data is frankly super messy. You've got to clean it, handle missing values, and normalize it. Why? Well, you don't want a massive number like square footage to mathematically drown out a smaller number like the total number of bedrooms. Step 3 is model selection. Since we're predicting a price, you choose a suitable algorithm for that specific task. Fourth is training. This is where the magic happens. You feed those house features and known prices into the model so it can learn the underlying relationships. Fifth is evaluation. You absolutely must test your model on unseen houses. You have to know, did it actually learn the market trends or did it just memorize the training data? Finally, step 6, prediction. Your fully trained model goes live, ready to evaluate brand new houses out in the real world.
Now for Section 3, regression versus classification. Whenever you're faced with a new machine learning problem, you always have to ask yourself one foundational question. Am I trying to assign a label, or am I trying to predict an amount? This one simple question splits the entire supervised learning world right in two. If your target output is categorical, meaning it falls into distinct, separate buckets, you are dealing with a classification problem. Is this email spam or not spam? Is the patient healthy or sick? Those are discrete categories. On the flip side, if your target output is a continuous number, well, then you have a regression problem, predicting the exact future price of a house, forecasting next month's sales revenue, or estimating a person's precise blood pressure. The type of output fundamentally dictates which specific mathematical tools you're going to pull out of your toolkit. Which brings us perfectly to Section 4, a deep dive into those key algorithms. First up is an absolute classic for continuous data, linear regression. Simply put, this algorithm computes the linear relationship between a dependent variable, the exact thing you're trying to predict, and one or more independent features. It does this by fitting a linear equation right to your observed data. Imagine taking all your historical house prices and plotting them on a graph based on square footage. Linear regression calculates a straight line of best fit that slices right through the center of all those scattered data points, perfectly tracking the overall trend. Now, if you only have one feature, like square footage, that's called simple linear regression. But if you start adding more features into the mix, like the number of bedrooms, the age of the house, the school district, it becomes multiple linear regression. It is elegantly simple, yet incredibly powerful for forecasting continuous trends. Now, our next algorithm has the word regression in its name, which can be a little confusing because logistic regression is actually used for classification tasks. Instead of predicting a continuous number, it predicts the probability that an instance belongs to a specific category. And it handles this in 3 distinct ways, depending on your target variables. First, there's binary or binomial classification. This is your standard either-or scenario like predicting success or failure. Simple enough, right? But what if it's not a simple yes or no? That's where multinomial comes in. This handles 3 or more unordered categories. Think of classifying an image as a cat, a dog, or a bird. There's no inherent ranking there. A cat isn't higher than a dog mathematically. And finally, we have ordinal. This is for 3 or more categories that actually do have a meaningful ranked order, like a customer survey response of poor, good, or excellent. Moving on, another incredibly popular algorithm is the decision tree. These are fantastic because they're super versatile. They can handle both classification and regression tasks. The source material beautifully describes a decision tree as a hierarchical structure that works just like a flowchart to make decisions step by step. You literally start at the very top at what's called a root node. This node asks a simple defining question. For example, is it raining outside? If the answer is yes, you follow a branch down to an internal node that might ask a follow-up. Okay, is it windy?
You keep following these attribute tests until you reach the very end of the line, which we call a leaf node. The leaf node represents your final, concrete decision, like take an umbrella. It's a remarkably intuitive algorithm because it closely mirrors how you and I actually use logic and deduction in our everyday lives.
Next, we're diving into support vector machines, or SVMs for short. Originally developed for binary classification, these are incredibly popular because they aim to rigorously minimize error. Imagine a 2D space filled with a mix of data points. Let's say a cluster of black balls on one side and a cluster of white balls on the other. Your job is to separate them. The ultimate goal of an SVM is to find the optimal straight line, which we call the hyperplane, that perfectly splits those two groups. But here's the kicker. It doesn't just draw any arbitrary line that happens to work. The algorithm mathematically positions this hyperplane so that the two distinct groups are pushed as far apart as possible from that dividing line. Creating this massive buffer zone is absolutely crucial for making confident, clear-cut predictions on new data.
Let's unpack the core spatial concepts that make SVMs so darn effective. We just mentioned the hyperplane. That is your central decision boundary. In a 2D space, it's just a flat line. In a 3D space, it's a flat plane. But the true secret to an SVM success is the margin. The margin is the actual measurable distance between the data points closest to the line, which are known as support vectors, and that central decision boundary itself. By intentionally maximizing this margin, you dramatically reduce overfitting. This ensures your model generalizes beautifully to new, unseen data. Now, we can try to achieve this through a hard margin, which enforces a very strict, perfect separation of the groups. But let's be real. Real-world data is messy. A single rogue data point can completely skew a hard margin. So practically speaking, we usually use a soft margin. A soft margin applies a little slack. It allows a few outliers or minor errors to cross the boundary. By ignoring those few rebellious data points, it creates a much more robust and reliable overall trend.
And that brings us to Section 5, Summary, and what's next.
Let's lock in your absolute key takeaways for Unit 3. First and foremost, never forget, supervised learning is entirely dependent on labeled data. You have to have that teacher providing the correct answers during training. Second, bringing a model to life isn't just throwing math at a wall. It requires a strict, non-negotiable 6-step workflow from meticulous data preprocessing straight through to your final evaluation. Third, always categorize your problem first. Are you predicting a continuous amount? That's regression. Are you assigning a discrete category? That's classification. And finally, you now understand the mechanics behind your core algorithmic tools. You're fitting mathematical equations with linear regression, navigating probabilities with logistic regression, charting logical human-like paths with decision trees, and drawing maximum margin boundaries with support vector machines.
So we've seen how phenomenally powerful machine learning can be when we have perfectly labeled data acting as our teacher. It's an incredible tool. But out in the real world, massive amounts of data, we're talking raw images, text, user behavior, they come with absolutely no labels at all. There is no teacher. So how can a machine possibly find patterns and learn from data when it doesn't even know what it's looking at? Well, that is exactly what we will uncover in our next explainer on Unit 4, Unsupervised Learning. You definitely won't want to miss it. Thanks for joining me today.
Hey everyone, and welcome back to the Explainer. Today, we are officially entering what I like to call the builder's arc of machine learning. If you've been following along with us, you know we've already looked at what machine learning actually is and how we go about prepping our data. But here in Unit 4, well, we're finally rolling up our sleeves and building. We're going to tackle 3 completely different, yet absolutely crucial stages of the machine learning lifecycle. We'll look at how to find structure in total chaos when we have 0 labels, how to force weak predictive models to team up and become absolute powerhouses, and finally, how to audit their work and measure their errors. It is a packed, super fascinating unit, so let's just dive right in. Okay, here's our roadmap for Unit 4. We'll start with a welcome and then jump into clustering with k-means. From there, we'll look at the power of ensembles, followed by a specific method called boosting weak models, and we'll wrap the whole thing up with measuring model errors.
Section 1. Clustering with k-means, finding patterns in the chaos.
So picture this. You've got a massive spreadsheet of customer data, right? Maybe it shows their ages and their incomes, but you don't know who the premium customers are or who the bargain shoppers are. You don't have any predefined labels or answer keys. How do you actually make sense of that data? Well, to solve that, we use unsupervised learning. Now, notice the contrast here. In supervised learning, which is what we usually hear about, you have an answer key. Every input has a known correct output label, and you're basically training the algorithm to map the input to the answer. But unsupervised learning,
That's a completely different beast. It explores patterns and associations in unlabeled data entirely without external supervision. There's literally no answer key. There's no teacher standing there saying, yes, that's a cat, or no, that's a dog. The algorithm is just fed raw data and asked to discover the underlying structure, the patterns, and the groups entirely on its own. It's pretty amazing. And this brilliantly illustrates exactly what we're trying to achieve here. If you look at the before k-means setup, it's just a scatter plot. It's really just a bunch of dots floating around in a two-dimensional space. I mean, to the human eye, you might be able to sort of guess at some groupings, but to a computer, it's just raw x and y coordinates. It's disorganized, it's total chaos. But then look at the after k-means state. The algorithm has magically partitioned those dots into 3 neat, distinct, organized groups, complete with a center point for each. It figured out how to assign each data point to a cluster based on its commonalities. In this specific case, its physical distance to the other points. It successfully separated the signal from the noise. But you're probably wondering, how exactly does it pull off this magic trick? Well, it does it through this brilliantly simple, repetitive loop. Let's walk through these steps together exactly as they're laid out in our syllabus. Step 1. You, the human in the loop, have to select the number k. And k is simply the number of clusters you want the algorithm to find. In that last example, k was 3. Step 2. The algorithm drops k random points onto the graph. We call these centroids. You can think of them as the initial, totally random leaders of our new clusters. Then we hit step 3. Every single data point in your dataset looks around and asks, hey, which centroid am I closest to? And it assigns itself to that closest one. Now, step 4 is where the actual learning happens. Now that we have these rough, kind of messy initial clusters, the algorithm calculates the variance. It finds the actual, true, mathematical center of all the points in that newly formed cluster, and it literally moves the centroid to that new center. Now we hit steps 5 and 6, which is the loop. Because those centroids just shifted, some data points might now actually be closer to a different centroid, so they switch teams. Then we calculate the new centers again, we move the centroids again, and this just repeats over and over until nothing changes. The centroids stop moving, no data points switch teams. When that happens, as step 7 tells us, we're completely done. The model is ready. It's just this elegant trial and error geometric dance that takes chaos and turns it into clean, usable clusters.
Section 2. The power of ensembles. Teaming up for better predictions.
Okay, so imagine you build a predictive model. Maybe it's a decision tree, but it's kind of weak. It makes mistakes. Instead of just throwing it in the trash, what if you built a whole team of weak models? That right there is the core philosophy of ensemble methods. As our source materials state, an ensemble approach combines predictions from multiple individual models to achieve better predictive accuracy and robustness than any single model could on its own. Think about it like asking a giant crowd to guess the weight of a cow at a fair. One person might be way, way off, but the average guess of 100 people, it's usually shockingly accurate. In machine learning, instead of relying on one single overly complex model that might just memorize the data and overfit, we use several weak learners. By aggregating their outputs together, we reduce errors, we minimize variance, and we create a highly robust super team. It's a real game changer.
Section 3. Boosting weak models. Learning from mistakes.
Now, within this world of ensembles, which includes other cool techniques like bagging and random forests, there is one incredibly powerful technique we absolutely need to focus on, and that is boosting. Boosting takes that team concept we just talked about and adds a brilliant twist to it. It's an ensemble technique that attempts to build a strong classifier from a number of weak ones. But here's the secret sauce. It builds them in series. In a lot of other ensemble methods, you might build, say, 100 models independently at the exact same time. But boosting, it builds them sequentially, one after another, with a highly focused purpose, to correct the specific errors made by the model that came right before it. Let's detail exactly how this sequential process plays out. Step 1. A first model is built from your training data. Now, because it's a weak learner, it's going to get some things right, for sure, but it's going to get a lot of things wrong. Step 2. The algorithm identifies exactly which data points were incorrectly predicted by that first model. Step 3. A second model is built, but this one acts like a specialized tutor. It doesn't just look at the whole dataset equally. It focuses extra weight and extra attention on the exact errors of the first model, trying its absolute hardest to get those specific tricky points right. And then, step 4. We just continue this procedure. A third model focuses on the second model's errors, a fourth on the third, and so on. These models are chained together in this way until the complete training dataset is predicted correctly or until we hit a maximum number of models that we set. By learning directly from its past mistakes and weighting those errors heavily, the ensemble literally boosts its way to incredible accuracy. Section 4. Measuring model errors, grading the performance. All right, so we've clustered unlabeled data, we've built highly accurate sequential boosted models, but here's the thing about machine learning. You never, ever just assume a model works. You have to grade its performance on unseen testing data. Our syllabus gives us a veritable toolkit of evaluation metrics to use for this exact purpose. I'll rapidly list them out here just so you know what's in the toolbox. We have accuracy, which is simply the total percentage correct. We have the confusion matrix, tracking our false positives and false negatives. From that matrix, we get precision, recall, and their combined harmonic mean, which is called the F1 score. We also have graphical tools like the receiver operating characteristic curve, or ROC, and the area under the curve, the AUC. And finally, we look at the overall distribution of errors. All of these metrics tell us different, really important stories about where our model succeeds and where it falls flat.
So the crucial point here is understanding the spread of those errors. And that leads us to zero in on one specific metric detailed in our sources, MAD. This can stand for median or mean absolute deviation. Let's focus on the mean absolute deviation for a second. MAD is defined as the average distance between each data point of the dataset and the mean of the data. Now, what is this actually telling us? Essentially, it represents the amount of variation that occurs around the mean value. It's a measure of spread. If your model's errors have a high MAD, it means your predictions are wildly scattered all over the place. Not great. But if the MAD is low, your errors are tightly clustered together. It tells us how consistent our data, or our errors, really are.
Okay, don't let the math symbols scare you off here. MAD equals the sum of the absolute value of x minus mu, all divided by n. I know, it looks like a completely foreign language, right? But it's essentially just a really simple recipe for calculating an average distance. Let's decode exactly what these pieces mean because it's actually super straightforward. Let's walk through these variables like puzzle pieces. First up, mu, that's that little U-shaped symbol, is simply the mean, or the average of your whole data set. X represents each individual observation or data point. So the core of the formula, x minus mu, is really just asking, hey, how far away is this single point from the average? We use absolute value bars, those straight vertical lines you saw, because we only care about the actual distance, not the direction. Being 5 units above the average or 5 units below the average is still just a distance of 5. Next, the sigma symbol just means we add up all those individual distances. Finally, you divide by n, which is just the total number of observations. So when you put it all together, you're literally calculating the distance of every point from the average, adding them all up, and dividing by the total. It is simply the average of the distances. It's a beautiful, remarkably simple way to measure spread. Section 5, the big picture, Unit 4 recap. And just like that, we've completely traversed the builder's arc. We covered a ton of ground and conquered 3 massive concepts today that fit perfectly into the machine learning workflow. First, we learned exactly how to find hidden patterns in complete chaos using unsupervised learning, watching k-means drop its centroids and loop its way to perfectly organized clusters. Second, we learned how to build predictive superteams with ensembles, specifically looking at how boosting hyperfocuses on correcting past mistakes to create incredibly strong, robust models. And finally, we learned that we must always measure our success, looking at our toolkit of evaluation metrics and breaking down the math of the mean absolute deviation to really understand the spread and variance of our errors. But before we wrap up, I want to leave you with a thought, a little warning to chew on as we prepare for whatever comes next. Earlier, we said that boosting builds models in series until the training data is predicted perfectly. But really think about that for a second. If a boosted ensemble memorizes its training data so perfectly by endlessly obsessing over every single tiny error, what happens when it encounters an unpredictable, totally new environment? Does it actually generalize well to the real world, or has it just memorized the past? That right there is the dangerous trap of overfitting, and it's something every single machine learning engineer has to battle. Thank you so much for joining me on this deep dive into Unit 4. Keep questioning, keep building, and I will see you in the next explainer.